Yes, thanks everybody. I'm looking forward to telling you a bit about what we're doing. And Ilaria has given the perfect introduction. A lot of basic stuff there that I'm going to assume you know, and Ilaria has dealt with that, so that's good. Many of you on this call probably have already come and visited us at my open air laboratory. IMPACT standing for Intensive Monitoring of Planted and Competing Trees. We're focusing on eucalypts. I'll tell you about that in a moment. And that site is based down here in our neck of the woods, just south of southeast of Stellenbosch, on a farm called Lawrenceford, near Somerset West. We've put down a 10-hectare compartment of eucalypts in a design which allows us to explore a whole lot of responses in trees and understand how these trees grow. Essentially, the core questions of the experiment revolve around how these trees respond to different spacings and how this happens across 4 cornerstone species. Now, some of you guys commercially will say, what on earth are we doing with those species? The species were chosen partly for commercial reasons, but partly also because we wanted to get maximized variability in biological response, and I'll come to that in a moment. But this experiment has this as a core underpinning. Ultimately, though, that's only the start. What we really want to achieve in the IMPACT Open Air Laboratory is an attempt at figuring out what's possible. We want to work out how much can we learn about these trees at the finest possible temporal time resolution, the finest possible spatial resolution. We really want to push the limits a little bit. And my personal research interests are in developing better models, better predictive models, moving into the 21st century as we are, where artificial intelligence and sophisticated modeling techniques are becoming the norm. We really need to up our game in our forest modeling space. And so one of the key elements of this project is to give us data sets that will allow us to model at the highest possible resolution that we can. So whilst the spacing and species questions give us a core underpinning, this experiment is about so much more than that. And another element that I really want to emphasize, and it ties in so beautifully to what Ilaria was talking about, that is collaboration. So I really want to encourage those of you, especially in the research space, who have an interesting research question, who want to get involved with us. The IMPACT Open Air Laboratory is something of a playground. And so we encourage you to contact me and see, well, what kind of interesting questions do you maybe want to apply to this problem? I also just a real shout out to Dr. Hans Merensky and the Hans Merensky Legacy Foundation, who fund most of this work, with some very significant funding also from Forestry South Africa through the SIF program, the Forestry SIF program. Without that funding, this work wouldn't be continuing. But coming back to the species, so we've got these 4 main species: Cladocalix, which is from the south of Australia down here. If you can see my mouse, which is a relatively drought-tolerant tree. It does very well in the Western Cape, actually. We've got 2 East Coast species, Eucalyptus grandis and Eucalyptus europhylla. Eucalyptus cloesiana grandis, many of you would know. Cloesiana is a very interesting one because it overlaps with some of grandis's range, but it's a very different animal, produces very high-density wood. And one of our questions was why? Why does it produce such a high-density wood? And then the last species, which you also know very well, is Europhylla, which comes from Indonesia. And so these 4 species, all really different cases, all doing very different things. And you can actually see on the left there, with some data from my MSc student, Aaron Ramsey, that they actually have very different seasonality, temperature, rainfall requirements. And so our site was really going to play some interesting games, seeing how they're all doing together at our site. Let's get to some remote sensing. Here are some satellite products. There's many of these products. I'm sure many of you know of these. One of those is the Worldview product. It's the top left there. That's used from time to time in Google Earth and Google Maps. It can potentially give you red, green, blue visible imagery down to about 0.3 meters, 30, 40 centimeters. So you've all seen that on your Google Maps probably. Sentinel-2 is another product where one can get free data from Sentinel down to 1 meter or 2 in resolution. And that's got multiple spectral bands. And then we've got, I mentioned here, this because it's a really nice graphic here, this Couva Space platform. This is one of the hyperspectral products available with a regular return interval, but quite big pixels, 10 or 15 meters, something like that. But you've got all these different satellite products. And so what do they do for us? Well, here's an image of my research site there in Somerset West, and you can see some satellite imagery from Worldview on the left, and some Sentinel satellite images on the next three in those top images. And you can see, of course, that they're highly pixelated. So if you look, here's our research site here and here and here, and we do learn something, but I'm interested in plot level. And in fact, I'll show you in a moment, I'm interested in tree level information. So the satellite data doesn't quite get us where we want to be. We've done some experimental playing around with another satellite product, a hyperspectral satellite product called Wyvern. They've got a series of products which they call their Dragonet series. And they get down to, they claim even 3 meters, but what you're seeing here in this bottom imagery is actually 5-meter pixels on our research site. And I think that's available in about 16 bands. I must just go back and check 16 spectral bands. And of course, the value of this, and Ilaria alluded to this, is that with the resolution of multiple bands in hyperspectral data, we can start to say very interesting things, even potentially going down to the point of distinguishing between species. But as you can see here, even with Wyvern, Dragonet satellite imagery, which is one of the best resolutions that I've been able to find, and it's very expensive, we still highly pixelated. So we're still not resolving that level that I want to see. So where do we go from here? Well, where we have to go is where Ilaria was talking to you about, and that's drones and airborne imagery and other imagery and other things which are limited. Some of the airborne solutions that we're using at our site include this hyperspectral camera, which was specially developed in a collaboration done with my colleague Anton Kunicke. That has to be mounted on a proper, good old-fashioned fixed-wing aircraft like this one. And we use a range of different drones. We use DJI products like the Phantom, which gives us multispectral data. We're using LiDAR-based drones and so on. And so let me show you what this means. So we can zoom in on our site with a satellite image, and we can see our site very nicely. This is a few months ago, by the way, when the trees were very little. But then we can actually start to zoom right in on the trees, right down to the leaves when we start to work with drones and other airborne imagery. And that brings me to our newest toy, which is another DJI product, which they refer to as the Dock 2. Now, the Dock 2 uses a good old Mavic-based, in this case, they call it the Matrice drone, which is a sort of Mavic, fancy Mavic, which gives us visible imagery only. But the cool thing about this is that we have one of these Dock 2s now on our site at our base station at the research site. And we can fly this drone whenever we want, as often as we want, as long as we want. And it can dock and charge and take off again and fly. And because of this, we're able to fly pretty cheaply, and we can fly low. And that means we're getting pixels of between 2 millimeters and about 5 or 6 millimeters for each drone flight. We can even go smaller than that if we want to, but it doesn't really get practical. And so you can see we're actually resolving individual leaves on individual trees, and we're doing this at least once a week. So what we're able to see then is how the trees are responding to very short-term changes, and even see individual leaves falling off the trees, and ultimately, potentially in collaboration with colleagues like at FUBI, we can start to see the emergence of pests and diseases and so on. So this is a really cool tool for us, very valuable. And you can see now that we can start to look at individual plots with this kind of resolution on a very regular basis. These images, by the way, have been generated by my very bright student, Jacques Vermeulen, and I give him all credit for the cool stuff that you're seeing here today. One of Jacques' pioneering efforts here is developing automated crown detection algorithms that you can see here, largely using free software after a lot of the processing is done. And I must say, by the way, that all this work is being done in collaboration with a company, Integrated Aerial Systems. Integrated Aerial Systems actually does all the flying for us. They do all the monitoring. They do all the maintenance of this drone. They did all the getting of permits, which was a hell of an issue for this drone because there's no pilot at the site. This is all being flown remotely from Cape Town. This drone gets launched from a place in Cape Town. A guy sits there watching it by video and lands it again. And the permitting of that is brand new. So this is something we could never have done without IAS. And I strongly recommend those of you who don't use drones on a constant basis to look at third-party partnerships for this kind of thing. They also do a lot of the initial pre-processing for us as part of the deal. So then what Jacques gets is fairly nice pre-processed data, and he's able to do the cool stuff, like look at how the canopy dimensions, tree heights, and so on are changing. So what you can see that Jacques is able to look at canopy dimensions. He's also able to get these fantastic height estimates of our little trees. The trees are still small. They're only a year and a half old. The trees are still small, but he can get this fantastic information about three-dimensional canopy attributes, which is very interesting for us at this stage, is how the canopy is developing, which is going to be a big part of our growth modeling. And Jacques able to then look at this, across our different plots, the 5 by 5 meters and the 1 by 1 meter. In this case, you're looking at mixed plots, mixed species plots. You can see the Europhilas, the Granduses, the different species. The red is showing high points, the yellow and so on is showing lower points. And this kind of data has been generated in a pretty much automated way from every flight, every week, which is fantastic, because you can imagine the kind of information we're going to learn about how these trees are growing. There's a lot of other things we can get. We can get, mini DEMs and all sorts of things from this. But that's not the only tool we're using. We're also using terrestrial-based scanners, and in this case, we're using a laser-based scanner. This is a Regal instrument here, very high-end Regal instrument, a time-of-flight-based instrument. This is one of the plots a few months ago. It's one of the 1 by 1 meter plots. You can actually see our central pole in the plot there, where we've got a set of sensors, which I'll tell you about in a moment. And this is now giving you a lovely overview of the trees. But what we can then do from there, and this is not the same plot, by the way, this is older Grandis trees. But you can see now that my PhD student, Urwasi Ngakana, who's developed all of this, is that he's able to set it up that he can actually extract individual crowns of individual trees, and we're able to get really the high resolution three-dimensional models of trees from this LiDAR. We're also, and this is important, when we run the scan at the appropriate settings, able to just about see individual leaves. You can see it's a little bit hazy, but what we're able to obtain quite successfully here is metrics like leaf angle and leaf density. So we can actually start to extract leaf level metrics from the LiDAR as well under the canopy. So that drone tends to not see very well under, but the LiDAR sees beautifully from in under. And this means we can develop better canopy development models than we've been able to do up till now. A third aspect that we are pioneering in collaboration with our colleagues here at Electronic Engineering is the use of autonomous robots with a whole range of sensors on them. And you can see here a few different robots are being tested by a master's student that I've got at the moment, Miss Mia Hum. Many of you might know Mia's dad. It's Corey Hum and her dad, Hanel Hum. Mia's now an MSc student with me who's registered at engineering. And she's developing which robot can potentially be developed into an autonomous platform to rove around the site and pick up, in this case, lower resolution LiDAR scans, but potentially with some interesting opportunities later. But what about this pixel to plot title of mine? Well, let me start off by saying that a lot of this data that we get from above or from the site has to be calibrated. And so one project that we're doing here as a bit of a lead up to that is being led by a MSc student, Peaceful Shangase. She's been co-supervised by my colleague Leandra Muller and Bruce Talbot. And she's doing work here in one of our scanning facilities, very, very new here, to get information about a range of different spectral responses on small trees. And you can see here, Peaceful's done an experiment to drought some trees and not drought others. And then from that, she's developed, using that scanner that you see in this slide, she has here developed a nice calibration value for normalized difference vegetation index. This is going to be very valuable to feed back into some of this drone data that we're going to be getting later. And that brings me to an important point, which I'm going to elaborate on in a moment, and that is that's multispectral data. That with hyperspectral data with appropriate calibration is an incredibly valuable part of what we're trying to do. And that's something that I'm, as difficult as it is and as expensive as it is very important to us. You can see here, when you actually get very high resolution spectra at the leaf level, that's the green curve, or good resolution data, the blue curve from a high-end hyperspectral sensor, that's the blue curve, or even the red curve, which is multispectral data. A lot about the response of canopies. And then we can start to link it back to stuff. okay, like Peaceful's work is going to do. And the other aspect of what we're doing at the IMPACT OAL is getting into the field to measure stuff. So what you can see here is some of our core measurements being done. In the middle there is my master student, Erin. Erin's just finishing up her master's. She got a distinction. She did a very, very good job. And this is some of the instrumentation she's been using in the field. These are LICOR instruments measuring incredibly high quality data on photosynthesis, stomatal conductance, basically how the trees' leaves are operating on a day-to-day basis to fix that carbon dioxide, turn it into sugar, and ultimately turn it into wood. And these are the things we want to measure from remote sensing tools, but we have to first measure it in the field. And she's generating incredible data. I won't go into the amazing detail here. I just want to impress you with the graphs really more than anything else, and encourage you to have an open mind to this kind of data set. But what we can see here are physiological metrics that tell us about the health and activity of our leaves. And all of these things are essentially metrics that can be derived from gas exchange measurements and response and fluorescence measurements that we're able to obtain. Many of these things we can obtain from remote sensing tools. And you can see how our different species and our different spacing start to separate out on these things. So we've got a great tool in the IMPACT Open Air Laboratory to get very different numbers that make for great collaboration and calibration tools, also collaboration tools, but calibration tools. Here's more of Erin's data. You can also see here how she's shown very interesting differences in the structure of the leaves here, for example, leaf mass and stomatal density. Ultimately, we also want to see how much can we calibrate these kind of metrics from remote sensing data of the right spectral resolution, the right temporal resolution, and the right spatial resolution. But none of that's going to be possible unless we've got high quality field data, which is the sort of stuff that students like Erin are producing. One of my postdocs is just finished, Edith Sinkini. Edith's just moved to Rhodes University, so it's great to see some of our Stellenbosch colleagues going off and really jumping in after having some really solid time in the forestry industry, going off and moving into other university environments. Edith's work focused on how leaf level responses adapted to pulses of rainfall after drought, not just long-term drought or long-term rainfall means, but what happens when you have a drought followed by a pulse of rainfall. These trees, these eucalypts tend to gallop. They sit and wait, then the rain comes and they gallop, and then they slow down again. So those pulses, those short-term events are very important. And that's what we also want to see at the IMPACT OAL is how did the tree respond to a short-term event? We're not just interested in long-term means. And Edith's gathered that kind of high-resolution physiological data, which we're going to link back to the remote sensing imagery that we've been able to acquire from our various platforms. In combination with this, we also have continuous monitoring happening at the plot level. And so you can see here a data logger that was developed in-house by one of my master students, Chris Erasmus. He's actually had multiple prizes for this, by the way. He's got a Blue Sky Award that was awarded by PAMSA. He's just got an incredible accolade from the UN FAO for an innovation in forestry technology for this product. It's a low power, low cost data logging system that sits in the field and transmits its data at low power across many, many kilometers using a wireless communication protocol called LoRaWAN. And you can see that what this little logger is doing, sitting in the field, we're building these things for sort of 2,000 Rand or less, and it's logging individual temperature profiles over time for all of our different plots, the different spacings for the different species, also logging water content in the soil temperature, relative humidity, and growth data. So you can see, for example, here, this is a little dendrometer that we fit to the trees, and this tool measures hourly variation in stem size, which gives us incredible insight into how these trees are responding to drought and temperature, and who knows, many other things. This is a very integrated signal. And so this all communicates back with that same little wireless system transmitted back to our central wireless system. But what this needs is, and Alaria alluded to this a lot, that it's all very well. We can collect these squillions of records of data, but we really find ourselves hitting the wall is with integrating it all. There's a couple of papers I refer to here, one by Erlich Sommer et al. And another one by Ramadan et al. I'll refer, if anybody wants this, I can send it. These papers start getting to grips with some of these problems. In one of these here, they're talking about illegal logging, but I mean, the applications are multiple. But you'll see all of these papers now talk about AI and data analytics and data management tools. And that's the key. And so we're using that same information hub platform that Ilaria mentioned as an integrating tool where our data are being stored. Our vision is for this to be open access, by the way. So people who want to work with us on this, we can give you access to our data sets, with appropriate understanding in place. And what we ultimately want to be doing is setting up artificial intelligence, deep learning, and other types of modeling platforms and profiles and solutions to integrate all of this. And I'm going to be appointing a new postdoctoral fellow in the new year, working with our agroinformatics teams and our School of Data Science to see how we can take this overwhelming amount of data, integrate it, and turn it into information that can support decisions on the ground later. That's all I have to say, Katie, if you want to take it from there.